Okay, we're going to talk about a few other expressions of energy, and we're going to base it on the ionization energy of the hydrogen atom. So in the previous video, I showed you that the ionization of the hydrogen atom is equal to the Balmer constant, 2.18 times 10 to the negative 18 joules. There's other ways of expressing this same energy, and this will allow us to basically come up with some conversion factors that will be rather nifty. And in some ways can be added to the ones that we talked about in the previous lecture. The first one is called the Rydberg. The Rydberg is rather simplistic. In essence, this is simply a means of saying, well, okay, 2.18 times 10 to the negative 18 joules is the energy of ionization of hydrogen, but instead of saying all that, let's just divide it by itself and call that the Rydberg. In essence, 1 Rydberg equals 2.18 times 10 to the negative 18 joules. And simply put, the ionization energy of hydrogen is equal to 1 Rydberg. But keep that in mind, 1 Rydberg equals 2.18 times 10 to the negative 18 joules. We could also re-express the ionization energy of hydrogen in terms of the frequency. We know that energy equals Planck's constant times the frequency. So divide the energy by Planck's constant and you'll get the frequency. So 2.18 times 10 to the negative 18 joules divided by 6.626 times 10 to the negative 34 joules second cancels out the joules and leaves us with 3.29 times 10 to the 15 per second or hertz. That will be the frequency, which is the expression of the ionization energy of hydrogen. We could also do the same thing for the wavelength. Simply cross multiply, so you end up multiplying by wavelength, you end up dividing by energy. So you have wavelength equals hc over energy. But we could also do something slightly different. We could solve for the inverse wavelength. Now the reason why we would want to even do this is because we know that the wavelength is inversely proportional to energy. So by simply taking the inverse of the wavelength, we have turned a value that was inversely proportional into one that now is directly proportional to energy. So the inverse wavelength is equal to energy divided by hc. And the inverse wavelength has a name. We call this the wave number. Alright, so, and typically we express it in the units given right here. It looks like mu with a hat. Okay, so mu hat, this is the wave number. And it's simply 1 over the wavelength. So we're going to utilize the information here. We know that the energy of ionization of hydrogen is 2.18 times 10 to the negative 18 joules. We divide this by Planck's constant, 6.626 times 10 to the negative 34 joules second, and the speed of light, 2.998 times 10 to the 8 meters per second. The joules cancel out, the seconds cancel out, and we're going to end up with units of 1 over meters. I highly recommend that you do use parentheses for every exponential number present in here as you do your calculations. Now here I'm also going to go a little bit further. I'm going to change the meters into centimeters. Notice that we have meters on the bottom, so we place meters on top. That's equal to 100 centimeters. This means that the wave number associated with the ionization of hydrogen is equal to 1.097 times 10 to the 5th inverse centimeters. That is another expression of the ionization energy of hydrogen. Another one that's quite often used specifically in physics is the electron volt. Now the electron volt is an energy associated with the charge of the electron as it goes through 1 volt worth of potential. But right here, as you can see, we can divide 2.18 times 10 to the negative 18 by the charge of the electron, and the charge of the electron is 1.602 times 10 to the negative 19. Joules divided by Coulomb is the same thing as volts. And here you can see volt times electron is what we call the electron volt. So divide 2.18 times 10 to the negative 18 by 1.602 times 10 to the negative 19, and you find out that the ionization of hydrogen is equal to 13.6 electron volts. Now, one thing that I should mention to you, and hopefully you have made that connection, is that all of the values that we're solving here are all equal to 2.18 times 10 to the negative 18 joules. So 13.6 electron volts equals 2.18 times 10 to the negative 18 joules. 1.097 times 10 to the fifth inverse centimeters equals 2.18 times 10 to the negative 18 joules. 1 Rydberg equals 2.18 times 10 to the negative 18 joules. So you could literally think of 2.18 times 10 to the negative 18 joules, the Balmer constant, associated with each one of the results right here. These are, in essence, your true conversion factors. Okay, let's convert this to energy per mole. We know that the energy multiplied by Avogadro's number can take the joules, which, by the way, joules is the same thing as joules per photon, multiplied by that number, that Avogadro number worth of photons. That will change the photons to moles, and change the joules to kilojoules. Simply divide by 1,000. And this will give you a value of 1312 kilojoules per mole for the ionization of hydrogen. All of these expressions, as stated, represent the same thing, the ionization energy of hydrogen. And 2.18 times 10 to the negative 18 joules equals 13.12 kilojoules per mole, 13.6 electron volts. 1.097 times 10 to the fifth inverse centimeters, 3.29 times 10 to the 15 hertz, and 1 Rydberg. So keep all these particular associations in mind. They'll be helpful whenever you're trying to juggle the conversion of units. But keep in mind that all of these units, with the exception of wavelength itself, are directly related to the energy. And you can definitely go back and forth between any of them. The ones that may be of most importance in this class are the kilojoules per mole, electron volt, and Rydberg, but I will probably ask you about frequency and wave numbers just the same, so don't discount them. Okay, so let's stop the video right here, and on the next video, let's talk about the emission of the hydrogen atom.